So in the last class, we discussed Cauchy sequence, and today we are going to discuss sequence divergence to plus infinity and then divergence to minus infinity. Okay. That's the topic. Sequences diverging. So when we say a sequence here to be divergent sequence, so sequence is not converges, then we say is a diverges. Diverging to plus or minus infinity. Okay, so what is the definition? So suppose xn be a sequence. Let xn be a real sequence. Be a real sequence. We say that xn diverges to plus infinity. We say that xn diverges to plus infinity, or simply say diverges to infinity. Okay, if you take any r greater than 0, we have to take the negation of otherwise you can take statement. So for any r greater than, for any r in r, there is a n in n. So after transit, all the xn's are bigger than this r. So there exists n in n. There is a stage capital N in n such that after this stage, that is such that if you take any n greater than or equal to this capital N, implies these xn's are bigger than this r. If r is any r, after certain stage, all the xn's are bigger than this r. That is not bounded above. It's increasing. Not increasing, but is after certain stage, everything is a bigger number. Okay, such a sequence is called a divergent sequence. So similarly, we define divergence to minus infinity. That is same thing for any r. There is a stage such that after this stage, all the xn's are less than minus r or less than r. Okay, if you take any r, here r there is no condition for r. Okay, r is any r, maybe positive or negative. Now, for example, if you take the sequence xn equal to n, so this sequence is diverges to infinity. Again, and if you take yn equal to 2 power n, this also diverges to infinity, because after steady state everything is bigger. If you give any r, we can always find, suppose so for xn, so this is 1, 2, sorry, this is 2, this is 3, 4, and so on. Okay, we are going to show this is diverges to infinity, that given any r, we can find a stage such that after this stage, all the xn's are bigger than this r. Suppose you are giving r is somewhere. Suppose I mark this is r. Suppose you are given r is like here. So after this, so I can find a stage. So I can find this is maybe some x, some l. Okay, it's an integer. Everything is integer, right? So I can find some another number x l plus 1 somewhere. Okay, now I can choose the stage is l plus 1. After this stage, r you can take this also, but better you can take this l plus 1. So after this l plus 1, every sequence is, if you take anything, is bigger than this r. Okay, given any r, suppose you are giving r is here. Suppose I can find so given any real number, so this is a result. Given any real number, we can always find an integer here, and then this is less than or equal, strictly less than, this is strictly less than n. So given any real number x, we can find a two integer. One integer is n minus 1, another this is n. So within this, we can find an integer n such that n minus 1 less than or equal to x less than. For example, given any real number. For example, suppose you are giving 6.7, we can find 7 here. 7 minus 1 is 6. So 6 less than or equal to 6.7 less than or equal to 7. So given any real number, we can always find it's bounded by integer. So given any r, we can find some integer here. Maybe this is some x, the sequence, because sequence is everything integer. Okay, so yes, some x, yes, another integer is x, s plus 1, like this. So after this s plus 1 stage, all the sequence numbers are bigger than r, because this xn is increasing 1, 2, 3, 4 and so on. Therefore it's a diverges to plus infinity. So similarly for these, again, if you mark the sequence terms on the real axis, so in the real line, so this is 0 and this is 1, but anyway the sequence starts from 2, 4, so 2, 4, 8, 16 and so on. It's powers of 2. And given any r, we can find a stage such that after this stage everything bigger than r. Suppose your r is suppose here. So anything, suppose for simplicity I am taking your given real number is here, r. So I can choose the fourth stage, because this is the first element, second element, third element, fourth element. So after the fourth stage, all the sequence numbers are bigger than this r. Suppose you are giving somewhere here r. So similarly, I can find some even number here and then some other even number here. Okay, we can always find some even number here, and that is power of 2, not even number. It's a power of 2 here. Some we can find a power of some 2 plus 1 something. Okay, so after this, now our stage is n plus 1. After this stage, everything is bigger than this r. So therefore, this 2 power n also diverges to infinity, plus infinity, because it increases positive side. Similarly, if we take a xn equal to minus n, it's decrease. Okay. Now I will ask one question. Suppose I give the sequence. Suppose if we take the even terms, the odd terms of the sequence are 1, and then the even terms of the sequence are 2k. The same the subscription. Okay, x2k is nothing but 2k. Now, is this converges to diverges to infinity? You got to mark the sequence terms. So what is the first term? 1. Second term is 2. Third term is 1. Fourth term is 4. Fifth term is 1. All the odd portions are 1. Even portions are multiples of 2. Okay, and so on. Therefore, if you mark here, this is 1, and the next sequence element is 2. Next sequence element is 1 again. The next sequence element is 4. Next sequence element is 1 again, and so on. So is this diverges to infinity? So that means what? Given any real number, we can find a stage. After this stage, all the sequence numbers are bigger than this r. Given any real number, is it true? No. Why? Suppose your real number, suppose here. Suppose we can find a stage, but not all the sequence number, because one sequence after this some stage everything contains alternately we have 1, right? So particularly this element not bigger than r. Yeah, after this stage all the sequence numbers should be bigger than r, but after okay, consequently or alternately we have 1. So 1, then sequence numbers are, suppose you find xn some xl here. So after that we have 1, and then xl plus 2. After that xl plus 3 is 1, but 1 is not bigger than r, because 1 is smaller than r. Okay, therefore this is not diverges to infinity. This is oscillate, a little bit oscillate. Okay, any doubt? But this is an unbounded sequence, but not diverges. Now we discuss some examples. Suppose a is bigger than 1, so then a power n converges to or diverges to plus infinity. If a is bigger than 1, implies that or then a power n is diverges to plus infinity, because a is bigger than 1. If a is less than 1, the a power n converges to 0. If a is bigger than 1, then a power n diverges to plus infinity. Okay, so how to prove this one? We can so a is bigger than 1, therefore a can be written as 1 plus some positive number, because bigger than 1, therefore a can be written as this one. So now what is a power n? Now raise the power on both sides by n. Now apply binomial formula for this side, 1 plus h power n. Okay, so actually this is actually greater than n into h, strictly greater than. This is actually Bernoulli's inequality. Okay, what is the Bernoulli's inequality? 1 plus x power n is greater than or equal to nx, where x is greater than minus 1. So whenever x is greater than minus 1, this is holds. So this inequality is called the Bernoulli's inequality. Therefore, this a-n's are bigger than n into h. Therefore, we can easily show that by Archimedes property, we can show that this is bigger than r. Given any r, since h is a positive number. So now apply Archimedes property. We got to show that a-n is diverges to infinity. That means what? Given any r in r, we got to find the stage n naught. I said after the stage, everything bigger than r. Okay, but by Bernoulli's inequality, we know that this a power n is greater than n into h. Okay, okay, no need to now keep this one. Now apply Archimedes property. So we know that a can be written as, because a is a number which is bigger than 1, therefore a is of the form 1 plus some number, positive number, where h is positive. Now apply Archimedes property to this real number. There is a natural number n in n such that n into h, which is bigger than r. Okay, but n, so now we can choose this stage. So this is our stage. Maybe I can take n naught. So for simplicity, I am taking n naught. So if you take any n which is bigger than or equal to n naught, so we know that n naught into h is bigger than r. So if you multiply h both side to this, we get a n into h also bigger than or equal to n naught into h. But n naught into h is strictly greater than r. But by this is greater than or equal to 1 plus h power n by Bernoulli's inequality. This is nothing but a power n. So after this stage, all the a-n's are bigger than this r. Therefore, a-n diverges to infinity, provided a is greater than 1. Okay. Now, the second example, if you take n factorial power 1 by n. So this diverges to plus infinity. Diverges to plus infinity. Okay, so since we are going to use the result, already I said that r power n or a power n by n factorial is converges to 0, because n factorial is converges faster than the power. Okay, therefore using this, we have a relation that given any real number, we can always find n such that n factorial power n is greater than r. Okay, so using this, we can show that this diverges to plus infinity. Anyway, keep in mind that n factorial power 1 by n diverges to infinity, but n power 1 by n converges to 1. Yesterday, we discussed that n power 1 by n is converges to 1, but n factorial power 1 by n diverges to infinity. Okay. Now, and then the third example, if you take xn is minus 1 power n into n, that is x1 is minus 1, and then x2 is 2, x3 is minus 2, and then minus 3, minus 4, plus 5, and so on. So therefore, this neither diverges to plus infinity nor diverges to minus infinity. Okay, but this sequence is divergent sequence. Okay, but divergent sequence, because it's not convergent, therefore it's divergent, but it's neither diverges to plus infinity nor diverges to minus infinity. So these are all examples. Suppose they will ask divergent sequence means you cannot say either it diverges to plus infinity or diverges to minus infinity. Even the sequence diverges, but neither diverges to plus infinity nor diverges to minus infinity. So this is an example. Okay, we discuss some exercises. So exercise, first exercise, suppose each xn sequence are positive, then suppose xn converges to 0. if and only if the 1 by xn, because each xn's are non-zero, therefore we can define 1 by xn. This sequence is diverges to plus infinity. If xn converges to 0, then 1 by xn converges to minus infinity. So this is a result. Okay, you can easily show that, because we know that this converges to 0 means what? All the xn's are less than epsilon for every epsilon. So therefore, you can take r equal to something. Therefore, you can take what is 1 by xn is greater than epsilon. Sorry, greater than 1 by epsilon. Okay. So take this one. So if you take epsilon is small number, positive but very small, then 1 by epsilon is very big. Okay. So therefore, if you choose r equal to then after this stage, all the sequence members of this sequence, which is bigger than r, therefore this diverges to plus infinity. Okay. That is because the xn is converges to 0. Therefore, each xn's are very small. That is the model. The distance between 0 and the xn's are very small. Therefore, this epsilon is very small number. But if you take 1 by epsilon, that very a big number. So therefore, we can get 1 by xn diverges to plus infinity. Suppose what happen if x is negative and then limit is converges 0. Suppose if each xn's are converges to, suppose the second case, suppose each xn's are negative and xn converges to 0, then what can I say about 1 by xn? Is minus infinity, diverges to minus infinity. Now, the next exercise. But in general, the converse need not be true. Okay, so this is very important that each xn's are positive. If each xn's are positive and the xn converges 0, then we can say 1 by xn converges to diverges to plus infinity. But suppose this condition violate, then this is not true. Why? Because if you take xn equal to minus 1 power n by n, so clearly each xn's are not positive, because we get a plus and minus term. But xn converges to 0. Then what about 1 by xn? 1 by xn is nothing but minus 1 power n into n. So this is a diverges to, is diverges or not? It's never diverges to, neither diverges to plus infinity nor diverges to minus infinity, because we get oscillate like oscillate minus 1 plus 2 minus 3 plus 1 like that. So therefore, we cannot say about the divergence of these sequences. Therefore, each xn is positive is very important. Even the xn converges to 0, we cannot say about 1 by xn converges to diverges to plus infinity. Okay, provided each xn's are positive. So this sequence is neither diverges to plus infinity or nor minus infinity. Okay. Okay, so maybe there are so many exercises there. You just go through it. Now we move to the subsequences. So subsequence means we have to take some if you take some subset of natural number, and then you will consider the function from the subset to R is a subsequences. Okay. So we define what is subsequences. Definition. Suppose we have a sequence, so we define x. So let x is a function from natural number to R be a sequence. X is a function, right? Be a sequence. Suppose we have a sequence, then what can you say about the subsequence? Then a subsequence is a restriction of this function x to the subset of n. So is the restriction function. So restriction means what? You have to reduce this domain into some subset. A is a subset of some natural number. Now, if you take domain is this A, then such a function is called subsequence. If you take natural number, that is a sequence. If you take any proper subset of natural number, then the function from A to R is a subsequence. Okay, if you take suppose A equal to set of all even numbers, that is a one subsequence. That is all even position you are taking. Okay, so the subsequence is the restriction function, restriction of X to an infinite subset. That A sub should be infinite subset to an infinite subset of infinite subset. I call the subset is S of n. For example, suppose you are taking our S is set of all even numbers. So S is set of even natural numbers. So set of even integers, positive even integers. Okay, anyway, of course, even positive integers. So suppose our original sequence is x1, x2, etc. and so on, then the subsequence should be only you can take the even terms, that is x2, x4, x6 and so on. So this is a subsequence. Suppose if you take x equal to odd integers, then you are taking only the odd numbers, x1, x3, x5 and so on. Okay. Suppose you are taking s is set of prime numbers, set of prime numbers. Then the sequence is x2, x3, x5. Only you can take the prime numbers, x7 and so x11, x13. So this is one of the subsequence. That is, we have to assign every element of S to the some real number. So the elements of S are 2, 3, 5, 7. Therefore, x2 is nothing but image of 2 under the function x. x3 is nothing but image of 3 under the function x, and so on. Okay, therefore, subsequence is nothing but, so given any sequence, the subsequence is nothing but the restriction function. You have to restrict the domain to the subset of natural number. That subset should be infinite subset. Okay. And you know already well-ordering principle. So what is a well-ordering principle? If you take any natural number, any non-empty subset of natural number, it has a least element. That is very important theorem, property, principle, well-ordering principle. Well-ordering principle. So what the well-ordering principle says, if you take any non-empty subset of natural number, or if you take any infinite subset of natural number, or if you take just, but if you take finite also, that is hold, if, suppose if you take S is a subset of natural number, be non-empty. If you take any non-empty subset of natural number, then it has a least element. This S has a least element. Least element means what? Smallest element. Then it has a least element. So that is what I am saying. That is, there is a element L in the set S such that if you take any element of S is always less than, greater than or equal to L. Such that if you take any X in S, L is smaller than all element of X. Yes. Okay, such an L exists if S is non-empty subset of natural number. But if you take any non-empty subset of integers, you will not get a least element. But if you take non-empty subset of natural number, you will get a least element. So this principle holds only in the subset of natural numbers, not for any other subset. Okay. Suppose if you take all negative integers, we cannot say least element. Okay. Negative integers. So therefore, this result is true only for natural number subset. So this well-ordering principle is very important. We using this, we can prove so many results. Okay, now here some lemma. Suppose a original sequence is converges, then all the subsequence converges to the same limit x. Okay, that is an important theorem. If suppose we have a sequence converges to x, and suppose we have a subsequence, and if I am denoting the subsequence x suffix nk. So is a subsequence. Then the subsequence also converges to the same limit. Then x nk is converges to x as k goes to infinity here. But here n goes to infinity. Okay. Because here the subscriptions are n1, n2, etc. Right? Therefore, here look like n is fixed, but we are varying the k. Therefore, as k goes to infinity, all the subsequences are converges to x, provided the origin sequence converges to x. Okay. So similarly, this is another important theorem, existence of monotone subsequence. So given any sequence, we can always find a monotone subsequence. So monotone means what? Either increasing sequence or decreasing subsequence. So, but the sequence is maybe or may not be increasing or decreasing, but we can find a subsequence which is monotone sequence. Monotone means either we can find a increasing subsequence or we can find a decreasing subsequence for any sequence. That is very important result. Okay, we state as a theorem. The theorem is existence of monotone subsequence of real sequence. What the theorem says? Given any real sequence, given any real sequence xn, real sequence xn, there exists a monotone subsequence. There exists a monotone subsequence. Monotone means what? Either increasing or decreasing subsequence. It's very important result. Okay. Now, another important theorem is Weierstrass, Bolzano-Weierstrass theorem. It says, suppose a sequence is bounded sequence, then we can find a subsequence converges to some point. That is convergent subsequence. But the original sequence need not be convergent. But if the sequence is bounded sequence, we can always find a subsequence which is converges to some point. But the original sequence need not be converges. So that is a theorem. That theorem is called the Bolzano-Weierstrass theorem. It's a very important theorem. All the named theorems are very important. So what is the theorem? Bolzano-Weierstrass theorem. So the theorem says if you have a bounded sequence, then the sequence have a convergent subsequence. Okay. So if xn is bounded, if xn is bounded sequence, bounded real sequence, then it has convergent subsequence. It has convergent subsequent. We can find a subsequence which is converges, but the original sequence need not be convergent. Okay. For example, we know that the oscillation sequence -1 power n. Alternately, we have a +1 -1, right? So, for example, if you take xn equal to -1 power n, so what is the sequence? Is -1 +1 -1 +1 and so on. So it's oscillate sequence. Therefore, but it's bounded by 1, but it's not converges. But we can find a subsequence which is converges. So we can choose the even numbers. So even position. So 1 1 1. So 1 1 1 is one of the subsequence. We know that this converges to 1. Or if you take -1 -1 -1 subsequence, this also converges to -1. So we can find a subsequence which is converges to some point, but not the same point. Maybe we can one sequence converges to some other point, another subsequent converges to some other point. Need not be converges to the same point. But if the original sequence converges, then all the subsequence converges to the same point. If the original sequence is not converges, then the subsequence maybe converges to some other point. Not all the subsequence converges. We can find a subsequence which is converges, provided the sequence is bounded sequence. That is important. That is Bolzano-Weierstrass theorem. So Bolzano-Weierstrass theorem, so many applications. So anyway, you have to remember the statement. Every bounded real sequence has a convergent subsequence. Now, one more theorem is that suppose xn is a Cauchy sequence. We don't know in general. I already said that Cauchy sequence need not be converges. Okay. Suppose there is a subsequence of a Cauchy sequence converges, then the original sequences converges. So I already said that convergent sequence are Cauchy sequence, but the Cauchy sequence need not be convergent. But in the real case, it is true. If and only if every convergent sequence is a Cauchy sequence, every Cauchy sequence is a convergent sequence in the real case. But in general, if you take a rational set or some other set, Cauchy sequence need not be converges. So, but when the Cauchy sequence converges, that is a theorem. Suppose we have a Cauchy sequence. Let xn be Cauchy. Okay. Let we have some subsequence. So let a subsequence x and k, at least one subsequence. Suppose we have a subsequence x suffix n k converges to some x. Converges to x, then xn converges to x. If the original sequence converges, provided at least one subsequence converges to x, provided xn is Cauchy. But in general, suppose xn is not Cauchy, suppose some sequence converges to x, we cannot say xn converges to x, because if we take the previous example. So we have some sequence converges to x, but the original sequence need not be converges. But if the given sequence is Cauchy sequence, then it is converges. But in the previous example, this xn equal to -1 power n is not a Cauchy sequence. Okay? Because this is a real sequence. If it is Cauchy, then it is converges, but the original sequence is not converges. Therefore, xn is not Cauchy. So suppose we want to find the limit of some Cauchy sequence, it is enough to find the limit of some subsequence. If you know limit of one subsequence, then we can easily say that the Cauchy sequence converges to that limit x. It's very useful result. Again, but in the case of real, if we take the Cauchy sequence in R, then automatically any Cauchy sequence converges to x. Okay, that is a trivial one. I already said, not trivial one, but it take fruit. Okay. Now there are some vessels are there. So okay, maybe we give some typical use of Bolzano-Weiss's theorem. Bolzano-Weiss's theorem says if it is bounded, then it has a convergent subsequence. But using this, we can prove that the sequence sin n sequence bounded, because sin is bounded by 1, right? So exercise use typical use of Bolzano-Weiss theorem. First example, suppose if we take xn equal to sin n, sin of n, we have to prove that this is divergence. Okay, actually this is a divergent sequence. Okay, but we can find a, suppose we have to show that xn equal to sin 1 by n has a convergent subsequence. How to prove? So the sequence, sin n has a convergent subsequence. But the sin n sequence, sin n is divergent, but it has a convergent subsequence. Why? Because of Bolzano-Weiss's theorem. Because sin is bounded. Sin of n is bounded by 1. Sin x is always bounded by 1, because the graph always oscillate between 1 and -1, therefore bounded by 1. So by Bolzano-Weiss's theory, if you take any bounded sequence, it has a convergent subsequence. Therefore, this sin n have a convergent subsequence, but sin n is divergent. But we have a subsequence which is converges. Okay. Now next, true or false. True or false. Suppose a sequence A xn is bounded. A sequence xn is bounded if and only if every subsequence xn have convergence subsequence. Every subsequence of xn has convergent subsequence. As a convergent subsequence. So this statement is true or false. So what is given that suppose xn is bounded if and only if every subsequence of xn has a convergent subsequence. Again we have a subsequence for the given subsequence. This is true or false. Again, if we take any subsequence of xn as a convergent subsequence, then can we say xn is bounded? Yeah, it's bounded. One way is clear. Sorry?
True, sir.
Why? What is the proof? True means you have to give the proof. False means you have to produce an example. So one way is trivial. So this way is trivial to proving this way. So we have to prove that xn is bounded. It is given that if you take any subsequence of xn as a convergent subsequence. Okay. So anyway, you can take the even numbers. All even sequence, this is subsequence. If you take all odd terms, this is also subsequence. And anyway, this is a convergent subsequence, therefore it's bounded. Therefore, this is bounded by some number, and this is bounded by the some number n. So therefore, we can take these two. We take the maximum of these two. We have xn is bounded. Xn is bounded by some number n. This L is nothing but maximum of m comma n. So this way is trivial. We take all the subsequence, convergent subsequence, then the sequence is bounded. But if it is given sequence is bounded, then we have to prove that if we take any subsequence of xn as a convergence because of Boltzmann-Weierstrass theorem. Because xn is bounded, therefore every sequence is bounded. If you take any subsequence, that also bounded. By Boltzmann-Weierstrass theorem, that subsequence have a convergent subsequence. Okay, therefore it is a true. Okay, so this is true. So now, this is one more important thing. Sequences defined recursively. Suppose using the previous two terms, we define the new term. Okay, we already defined like this type of sequence. So for example, Fibonacci sequence. So we define the sum of the previous two terms and so on. Okay. So now, what is the limit of such a sequence? Okay. So now I'm asking the question. It is asked in the some examination. I will state that what is it. Okay. So what is that? Sequences defined recursively. So for example, it is given that x1 equal to maybe they give some starting point. Suppose x1 equal to a, x2 equal to some b. So after this, we define xn plus 2 equal to sum of the previous two terms, that is xn and xn plus 1 divided by 2 for n greater than or equal to 1. For n equal to 1 means x3. x3 is nothing but a plus b by 2. And x4 is nothing but you have to again add the previous two term and then you have to take the average. Okay. So that means if you mark it, suppose a is here, the first term a is here, b is here. This is the first term x1. This is x2. What is x3 is nothing but average. So therefore this is our x3. What is x4? Average of x3 and x4. Therefore this is our x4. What is x5? Average of midpoint. That midpoint of x3 and x4. We have x5 is here. So what is x6? x6 nothing but this midpoint. The x7 is here and so on. Okay. So this is a. So what can you say about this sequence now? So after certain stage, all the sequence numbers are very close, right? Got it? So we can take average after certain, sorry?
Cauchy sequence, sir.
Yeah, Cauchy sequence. So after certain stage, all the sequence numbers are very close. So that much close you want, accordingly we can choose the stage. Okay. So therefore, clearly this sequence is a Cauchy sequence. So what is the length? What is the distance? We can find a b minus a by 2 power n. Like that we can find 2 power n. Okay. Anyway, so therefore, is a Cauchy sequence. Therefore, converges because it's a real sequence. Everything is a real number. It's a Cauchy sequence. Therefore, it is converges. Then, what is the limit of this convergence sequence? So the limit is, I am directly right, is 1 by 3. So therefore, this now the sequence xn converges to 1 by 3 times a plus 2b. Okay, this is standard example. Suppose we define x1 equal to a, x2 equal to b, then xn plus 2 is nothing but average of previous two term. Then the sequence is Cauchy, therefore converges. The convergence point is 1 by 3 times a plus 2b. Okay. So, but the proof is very difficult to this. Okay. So keep in mind this limit 1 by 3, 3 into a plus 2b. Now we have another sequences. This is the first example. Suppose we define another sequence recursively. So this actually sequences defined recursively. Recursively. So how is the spelling? Recursively. Yes. Recursively. Okay. So the next one. Suppose I take the first x1 is 2. Okay. In general, I define xn plus 1 is 1 by 2 times xn plus 2 by xn, where n greater than or equal to 1. So x1 is 2. What is x2? X2 is remember you have to substitute n equal to 1. Therefore, this side is we get 1 by 2 times 1 plus 1 by 1. Sorry, 2 by 1 is 3 by 2. So x2 is 3 by 2. So and so on. Now, what is the limit? So we can easily show that this is convergent. Okay, and then this converges to actually we have some point. So if you study the numerical methods, we can easily show that this converges to root 2 actually. Okay. Okay, how to find the limit? So take this one. Now, assume that xn is converges to some point, maybe I call L. So we got to find that what is that L. So since xn is converges to L, then xn plus 1 also converges because this is nothing but this is a subsequence. Here we start from x1, here we start from x2. That's it. You are just to omit the first two terms. That's it. So anyway, the converges same point. So by algebra of limits, look at this. So this is equal to the left hand side converges to L because xn plus 1 converges to L. This is equal to 1 by 2 is a constant plus by algebra of limits. So xn is converges to L plus 2 by xn is converges to L. Okay. Now simply with this cross multiply L, we get L square and then multiply by 2 L square plus L square plus 2. Right? So L square, or I did any mistake? So just to cross multiply, if you simplify otherwise, first you multiply by 2, so we get 2 times L equal to L plus 2 by L. So if you simplify this, we take the LCM is L square plus 2. Okay. So therefore cross multiply this L square. We get 2L square equal to L square plus 2. Therefore we can cancel 1 L square. Therefore L square equal to 2. Therefore what is L? L is plus or minus root 2. But all the xn's are positive. Since x1 is positive, that is 2. If you take x n general xn, because this is a positive number and this is a positive number, therefore sum of this also positive. Therefore finally this is also positive. Therefore each xn's are positive. Definitely it converges to, or at least because if you draw this one, that never converges to 0. So but the L gave 2 value plus or minus 2, but it's never take the negative value. Therefore this L should be root 2. Therefore this sequence xn converges to root 2. Okay, this is the idea. So maybe we'll solve similar problems. If the defined sequence recursively, if it is converges, we can easily find the limit. So exercises. First one. Suppose x1 equal to root 2.
Sir,
Yes. Yeah, tell me.
sir, actually now 11 o'clock we have a online class, sir.
Okay. So we can stop now.
Okay, sir.
We will discuss afternoon. We are free, right?
Yes, sir.
Okay, we will